Eu tô tentando ver. Okay, good morning. Welcome to the second day of Carlos Fest. I was asked to give 3 announcements. They're all here, but I'll read it anyway. So the first is that the discussion on the math teaching this afternoon will be in Portuguese. It's from 4 to 5:30 p.m. The second is that the cocktail has been rescheduled. It will now begin at 6 instead of 6:30, also today. And the last one is that the conference photo will be taken in front of this building during the afternoon break tomorrow at 3:30.
Where is the cocktail?
So the cocktail is at the Decanato do CTC, which...
Explain how to get it.
I cannot.
No. The locals can help. Come on, Carl. And the locals know. The locals know. Yeah, yeah. The tallest floor, the tallest building on campus. Yeah.
There's a map and it's a
Yeah.
I have to make a request. I have this fantasy that we should have a picture for the conference, right? Of a different nature. We should sort of mimic this painting by Raffaello, the School of Athens. Where you see all those mathematicians and philosophers talking to each other coming down the stairs.
Oh, I want to be.
So please get your robe.
I want to be Diogenes. I don't need. I want to be Diogenes. I don't need a robe. Yeah.
Okay, so before we derail the next talk, it's a great pleasure of mine to introduce Roberto. He is a professor at IMPA, but more importantly for this festivity, he also studied at the Curvature Institute. Roberto, feel free to...
And at PUC, right? So,
and at PUC, yes.
Yes, so... Well, of course, thank you all for being here. Thanks a lot to the organizer for this invitation. Thanks to Carlos for everything. We're going to be more specific about that in a minute. I mean, as I was reading the website for the conference, I realized that it didn't quite fit the description, the theme of the meeting, right? So, which made me slightly uncomfortable. But then I realized that maybe I can get a bit personal, at least for the beginning of the talk. And, this is just a picture of a picture, so the resolution is not very good. I mean, it's hard to... I can probably tell that Carlos and Ricardo are in this picture. There's also Léo Navarro, who's now Professor PUC, UFI, Max Souza, who's also there. And I mean, it's... I don't have a simple way to explain Carlos's influence in my life. I mean, I was never formally his student. I did take a couple of classes from him. But I was never advised by him in any sort of formal capacity. But of course, when you have a guru, you don't need to have a formal relationship, right? So there's so many things I learned from him. And somehow this picture, which was taken at PUC, and it's somewhere in that coffee room upstairs in the math department. I mean, I don't know, looking at it, I think of the many times when I walked around campus with Carlos, I mean, for different reasons. Sometimes you just say, come along with me, right? And it was hard to walk because you had to stop every 3 meters to talk to somebody who would come and say, hi, Carlos, long time no see. Or, Carlos, we need to get something, or we need to do something about the committee or whatever. So I think that, you know, beyond all the mathematics, and if I have to talk about the math, I mean, I remember he was the person that made linear algebra a respectable subject to me. So maybe that's saying a lot. But beyond that, right? Though his relationship to the university, his efforts to, you know, make things work, his relationships there also, struck me as quite significant. But also, I mean, walking along Capo, being invited by him to go to different meetings, gave me an opportunity to see him in action. And here's something that I heard from him. I mean, he attributed this quote to Sigmund Freud in a meeting that must have been, I mean, I didn't manage to locate the source for the quote, right? So, I mean, this, and I'm paraphrasing from memory, so maybe I'm not being quite precise here.
It's true, it's true.
Yeah, right? So, and you actually, I mean, I heard this from you in this very room. I don't know why, right? I was taking analysis 1 from you, I think, at the time. And you told the students, now we're going to have a meeting about, best practices for undergraduate teaching in the ciclo básico, right? The first 2 years of the undergraduate degrees in engineering, math, and physics, and all sorts of, anyway. But, and people were, they're coming up with all sorts of different ideas to get students more engaged and things. Well, maybe if we have a computer demonstration of something, maybe if we had a class that's called Introduction to Engineering and sort of shows the different facets of engineering, we're going to lose less students. And I mean, they're all trying their best somehow, right, to address real problems. And what I got from Carlos' intervention was that, nice intentions sometimes are not enough, right? And you're fighting against powerful enemies, for instance. I mean, I don't think he specifically meant drugs or narcotics, but he meant that, life can be, maybe, just maybe, right? So calculus and physics are going to be demanding subjects for all students, regardless of what you do, right? And you should keep that in mind. And here's something else that I was going through a memory. I mean, it has to do with one of the speakers in the workshop. I was about to go to Quran, I think, or maybe I was asking for a letter of recommendation to go there, from Carlos, of course, which I think was very helpful. And he made this pun. I mean, you might not know who Lupe Miranda is. This is a gentleman over here. This is from his Wikipedia page. He was probably Brazil's, I mean, I don't want to rank musicians, but I'm going to do it just for the purpose of brevity. I mean, he was maybe Brazil's best-known mandolinist before Jacó do Bandolim, which was somehow more famous, right? And I mean, I use this to illustrate the fact that, you talk to Carlos and you get his, little, well, I don't want to call them nuggets, but you'll get this little piece of knowledge that he seems to have about all subjects he could think of, right? They just come out naturally from him. I mean, I don't think that many people at PUC or elsewhere at the time knew who Lupe Miranda was. I mean, I did because I was a choro junkie, you could say. But it was just, I mean, it's just one of the great pleasures of speaking to him is that, you learn a lot, right? But it comes out in funny or interesting, unexpected. Right. Okay, but yeah. So now let me move on to the actual talk. So I'm going to be talking about work that I did with two, young colleagues and a more senior colleague. Sorry, this is the wrong picture. So this is work that Carlos did with somebody else, right? This is work that I did with somebody else. It's not, and then they joined forces somehow. So this is a true picture. So this is joint work with Dani, who's, I'm not sure the affiliations are quite correct because Dani has just arrived in Singapore. I'm not sure he's started that yet. So Zoraida is about to start. My baby hasn't started at Bocconi. And Gabor is where he's always been. So this is a talk about this concept of Fréchet means, right? So if you have a title and there are words in the title that maybe don't make sense to your audience, you should at least try to explain what they mean, right? So let me try to tell you that. But before I do that, this is a talk in probability. So we have a probability space. I'm not going to mention it very often. It's just a measure space for the analysts in the audience. And of course, the expectation of a random variable, by which I mean a measurable function from this probability space R, is just an integral, right? The integral of this function. And of course, this needs to be well defined, but yeah, let's skip that. But the mean, this expectation, there's another way to characterize it that works as long as your random variable, your measurable function is in L2, which is that you can write it as a solution to a minimization problem. So this is a simple calculation that you can give to your undergraduates, right? That shows that if you put a constant here, C, the expectation of x minus c squared, well, there's a piece that's just the variance, so it's fixed. And there's a piece that's the distance between the mean of x and c squared, right? So from this formula, it's clear that the only minimizer, the only c that minimizes this expression is the expectation of x, is the mean of x, right? And the reason why I'm mentioning this is that you can somehow make sense of this in any metric space. So now I have a metric space, and I have a random variable x that takes values in the space. So it needs to be measurable and whatever, right? And I'm just going to assume for simplicity that it's square integrable, which means that you take the distance from the random variable x to a fixed point, square that needs to have a finite integral, okay? And of course, if this is true for some point, it's true for all points. That's easy to see. And a Fréchet mean is just a minimizer of this expression here, right? So if we go back to the previous slide, the only minimizer is the expectation of x. So if you're on the right, so if you're on the real line, so this generalizes the notion of expectation of the real line. And it turns out that it also generalizes what would be kind of the natural expectation for vectors, right? So I take RK with the Euclidean metric, or sorry, there shouldn't be a square here, right? But anyway, so, and you can make a calculation that's similar to what you have in the real line, basically because when you look at the squared norm, right, you have the sums of coordinates squared, so it's really the same thing. And you get this formula, and again you get something that's fixed, plus something that's the distance between the c that you chose and the expectation of x, which is really the coordinate y's mean of x, and squared, right? So the only minimizer, again, is just the expectation of x in this coordinate y sense. But of course, there are other spaces that I might think about. I mean, statisticians sometimes think like things like the sphere or well, in this case, a circle, right? Just because you want to look at directional data for something. And then the Fréchet mean can behave quite differently. So if you look at a distribution, say that's uniform, right? There's just Lebesgue measure over this interval normalized. With the arc length distance, I mean, this is really isometric to an interval. So the Fréchet mean is easy to compute and it's unique. On the other hand, if you have uniform distribution of the whole circle, then every point is a Fréchet mean, right? And then, well, okay, if you were, I'm guessing we're all mathematicians here, so maybe motivation doesn't matter as much as for other audiences, but if you want to know why people care about these things, well, one simple reason is that, you know, like when you talk about data in real life or random phenomena, talking about the mean is one, you know, the mean is one object, one number that you can attach to your data or to your distribution that gives you some information, right? It might be more or less informative depending on context, but it's nevertheless gives you something. And the Fréchet mean can play a similar role for non-Euclidean data. And then there are all sorts of fancy things that have been done recently, especially by people around Hans-Georg Müller, who was at UC Davis, but also others. And I mean, also people in machine learning have been using Fréchet means for different things. I mean, I'm not going to spend too much time on this. But there is one metric space that I want you to keep in mind because it's an important source of examples for us, which is this L2 Wasserstein space. So what is Wasserstein space? You look at RK and you look at all probability measures of RK. So non-negative measures with total mass equal to 1. We're looking at measures that have finite second moments, meaning they integrate the function norm of x squared. And then the distance between two distributions, well, now I'm cheating a little bit because I'm going to define the distance only in the case where P is absolutely continuous with respect to Lebesgue, right? And in this case, the distance is the solution to a minimization problem, which is you look at all measurable maps that carry P to Q, right? So that the push forward of P is Q. And you choose the one that minimizes this, well, transportation distance, right? So you can think that P is a probability distribution, so it's a distribution of mass like a pile of sand. Q is another pile of sand. What's the optimal way to move the grains of sand around so that you minimize the mean square displacement? Right?
And T is measurable or what?
Yeah, T is measurable. Yeah, T is Borel measurable.
It doesn't have to be nice.
It doesn't have to be nice. Well, let me get ahead of myself and mention there's a very beautiful theorem that says that when P is absolutely continuous, you can actually show that the optimal map is always the gradient of a convex function. So it's nice in this sense. Okay? But there's a theorem by Young and Brenier, but which I'm going to come back to later. So there is a lot of structure somehow behind. For the minimizers of this problem, there's a lot of structure. And I mean, if you know more about P, say that it has a smooth density, then maybe you can prove that you get the gradient of a smooth convex function and things like that. But I'm jumping ahead now, right? So, and let me just mention that if you want to talk about a P that's not absolutely continuous, then you have to work a little bit harder. Then basically, you have to allow for what are called couplings in probability, but let me not, right? Because if you think about a point mass at a delta at a point is a measure, right? How are you going to transport that to, say, uniform measure over an interval, right? So you have to allow for more general transportation strategies, let's put it this way. But I'm not going to get into that here. So yeah, this Fréchet means, so this gives you a metric, right? I didn't say it explicitly, but it's this is a complete separable metric space with all sorts of nice properties. And it has lots of applications to things like when you're doing, statistics with data, there's actually probability distributions. The distribution of mortality, right? So how people in different demographic groups tend to die, at what age or what day of their lives they tend to die, things like that. And there are other problems where you're looking at things like, one very nice example of what they call space information in this paper that I'm mentioning here is like, when you have kids, you go to the pediatrician and you see these curves, right, that represent normal growth, of height and weight of the child, right? So, and oftentimes the curves for different children are similar, but they can be kind of deformed in space in the sense that maybe the growth spurts of each child do not occur at exactly the same time, right? So somehow you can model these deformations using, right, you can think of these curves as cumulative distribution functions, which are kind of related to probabilities, and you can model these things by saying that the curve was sort of, the x-axis was sort of randomly transformed, and that brings you somehow to this Wasserstein distance. And then, let me jump straight ahead to the picture, and then people use also this metric and image analysis. So what do I have here? So, here, suppose I have a database of images. Here I just have 4. And somehow I've normalized the images so that the total pixel intensity in each image is the same. So I can think of these things as mass distributions, probability measures over the square, right? So I have this database, and somehow I want to get some information. I want to get one image that somehow represents my database, right? And there are different things you can do. This thing here corresponds to looking at the pixel intensity at each point and just averaging it. So we're averaging numbers at each point, right? And this thing corresponds to saying, well, this is a probability distribution over probability measures. So it's a probability distribution of a Wasserstein space, and I'm going to compute the Fréchet mean. And I get something that actually looks like the butterfly that you would expect, right? So this is kind of an intuitive way, a picture is worth 1,000 words way to say that maybe a Wasserstein. Oh, because it's like you're seeing the butterfly moving around, right? So it's something like this. So, it's not going to be perfect, right? So, but it's, I'm trying to do something very hard. I'm trying to take an average of many different images that differ in all sorts of details, right? So it's not, if you had just translations of one of these images, then you get exactly an image like that. On the other hand, if you don't, then, there are things like these things in the wings that are going to make, that somehow come out as blurs here. And this, when you talk about something to students and then they have lots of questions, sometimes you have to start throwing books at them so that they'll stop, right? So that's what I'm doing to you. Right now, if you're interested in these things, these books look at, optimal transportation, which is this Wasserstein business, from different perspectives. So this is more like analysis in PDEs. These two are more like in statistics, but also, this is especially nice. It's all self-contained. So all the hard math I'm going to talk about, well, most of it anyway, is contained here. So we're mathematicians. We might be worried to know when Fréchet means actually exist, right? So uniqueness is delicate because, as I told you on the circle, right, there's no uniqueness, so you have to impose some restriction. But existence, oddly enough, when we started writing our paper, which is, I guess, all written but for the introduction, we didn't know that there were any results out there that guaranteed existence in a broad enough setting. It turned out that Adam Jaffe, he put out a preprint in the archive that we weren't aware of, but we have slightly different results saying basically that if you have a complete separable metric space, well, I guess Polish, right? That's what it's called. And there's some sort of weak topology for balls that make the balls compact and make the distance function lower semi-continuous. That's enough. That's a bit too much to get to grasp in one go. So let me just say that for all examples I'm going to be considering, so RK, proper metric spaces, right, where closed balls are compact, separable reflexive bonding spaces, Wasserstein spaces, they're all good from this perspective. So Fréchet means exist in all these spaces.
Is taxicab math?
What was that?
Taxicab math.
So that's a delicate case because it's separable, but in infinite dimensions anyway, it's not going to be reflexive, right? So So sorry, I was thinking of L1 really, right? L1 over the interval 0, 1.
If Polish and favorable, what is it that goes wrong there? What?
Oh, the closed ball is for you have a metric.
It's just in the example, right?
What was that?
Yeah, it's not reflexive, I understand that. But what about being Polish and favorable? It is.
So, sorry, favorable means what's in italics here, in gray. That's a name that we came up with. Favorable means that for every closed ball, you have a topology that you put on this ball that makes the distance, the function that computes the distance to a fixed point, lower semi-continuous. So if you think about, say, a Banach space, why is this true in a reflexive Banach space, right? Because the distance is a supremum over linear functionals of something, right? So, and linear functionals are continuous in the weak topology. And so the supremum of continuous things is lower semi-continuous. So that's the kind of example that we have in mind. Right, but I mean, I'm talking a lot about statistics and statistical applications, so maybe I should tell you, well, if you want to estimate the Fréchet mean in practice, what do you do, right? So, well, the usual setting for statistics or for much of probability is that you have independent and identically distributed, that's what i.i.d. means, random variables which all have the same distribution as x, which really means this: I ask what's the probability that x1 lies in set A1, x2 lies in set A2, and I think that's going to be a product of things, and each one of them has x here, right? So that's my data. And how do people usually estimate the Fréchet mean from data? They just say, well, you replace, right? We had an expectation in our definition, so it was a minimization problem with an expectation. I replace this expectation by a sample average, right? Which is what you do because, well, for each fixed c, the expectation of this is exactly this expectation of distance squared from x to c, so that should be closed by some sort of law of large numbers, right? Now, of course, there are kind of the usual questions that people ask. Does this thing converge to the true Fréchet mean? I mean, that can be delicate also because Fréchet means are not unique, but when they are, does this converge? And then you want to know things about the distribution of the distance from this to the true Fréchet mean, all sorts of things, right? So the kinds of questions that would be the law of large numbers and the central limit theorem, more standard settings. And there's a lot of work on this here. Just have a few papers, a few recent, a few not as recent, but about all these sorts of questions. But really the point of the talk is that somehow there's a better way to estimate the Fréchet mean. And it has a certain number of properties that, well, first of all, it concentrates very well. It's robust. And as I said, it's different from the sample Fréchet mean, right? And I've just thrown this in your face knowing that I've just, I told you in the beginning I want to explain the words in the title of the talk. And of course, I have a bit of a setback now because I've introduced lots of terms that you don't know what they mean yet, right? So what is this sub-Gaussian concentration? What is robustness? I mean, as I said, right, so the estimating Fréchet means has to do a lot of the geometry of the space. So what kinds of geometric conditions do I need? And what's this estimator that's not the Fréchet mean? So let's go through that. So maybe I should ask, how much time do I have? I don't know what time we started. So if you tell me now, I should be fine.
Half an hour.
Half an hour? Good. Okay. Right, so here's the formal mathematical problem we want to solve. And so I have i.i.d. copies of a random variable x. I'm always going to be working in settings where the Fréchet mean exists and is unique. Okay? And I want to design a function, just a measurable function that takes data points and produces me what I'm going to call an estimate of the Fréchet mean. And the property that I'm looking for is that, well, it's kind of what you could call a high confidence, low error estimate of the Fréchet mean. So I fix a confidence level 1 minus delta. That's the probability that I'm allowing for things to go wrong. And I want to get the smallest possible error under this confidence. Right? So this R will depend on delta, depend on n, will maybe also depend on properties of the distribution of x. Right? So that's the kind of problem that I'm interested in.
You want to make R explicit?
As explicit as possible, yes.
It's space of this one.
Yeah, so I mean, we're going to get results that are not quite the optimal results, but they're optimal up to constant factors in certain settings. So that's the kind of thing that we're aiming at. Okay, and I'm going to be a bit more precise about that later on. So, well, in the one-dimensional case, well, what does this amount to, right? So we know that the Fréchet mean in one dimension is just the expectation, usual mean. If you look at what the sample mean is, it's just the usual sample average, right? You have your sample points and you average them. That's what the Fréchet mean of the sample is. And we know by the law of large numbers that this converges to this. Let's assume finite variance. So, and let's look at the behavior of this from this perspective, right? So that's, well, first of all, we know that in the limit, when n goes to infinity, this x bar of n, which is the average again, right, of these random variables x1 up to xn, it converges in distribution to a Gaussian. And then if you work this out, well, I mean, this tells you that you can put something here that's like standard deviation divided by square root of n times a function of delta that for small delta, which is the main case for us, really looks like this. Okay? Now, there's also a worst case bound that we learned when we're taking our first class in probability, which is Chebyshev's bound, which is, well, something that you compute in terms of variances. I mean, you might have not have seen it in this form, but just a bound that tells you, you know, that if I have random variables with finite variance, the distance to the mean satisfies this inequality. And now, of course, there's a gap between these things, right? This has a square root of log of 1 over delta. This has square root of 1 over delta. So this Chebyshev is much worse. But it turns out that this is unavoidable in the following precise sense. I'm looking for non-asymptotic bounds. For each n, I want to have an estimator, right? So if I give you an n, if I give you a variance sigma, or a standard deviation sigma, you can always come up with a distribution that's going to saturate Chebyshev's bound. So notice that it's different from what's on your left, which is this thing here, because here I fix a distribution and then it goes to infinity, right? Here I'm saying for each n and each delta, you can come up with a worst case distribution. But it turns out that this is an artifact of using this as estimator. So if you allow yourself to change the estimator, you can re-obtain this behavior, the sub-Gaussian. That's why we call it sub-Gaussian, right? Because it's close to the Gaussian somehow, right? It's the same grade as the Gaussian. And this was first figured out by Olivier Catoni, but then his construction was improved by Elian Valiant. So it's just, I mean, it's kind of amazing because it's, in some sense, the simplest problem you can imagine in statistics. You want to estimate the expectation of a random variable. And, you know, 13 years ago, people were still proving new and surprising results about this, right? And so that's what we're going to call sub-Gaussian estimate. So when you have this log 1 over delta on your confidence, dependence on your confidence parameter. And these bounds, they work for any finite n. They allow for very small delta. Basically, as long as delta is not exponentially small in n, you can get something like this. And it's crucial that you can design the estimator. You don't just take the sample mean, which is what people, you know, do all the time. You're able to design something. And then, so when Catoni wrote this paper, I think he was very proud of his achievement, right? But I would be proud too, I guess, because it's, as I said, right? It's let me go back to this, right? It's saying, okay, the estimator that everybody uses is somehow bad, but there's something you can do about this, right? And he wrote a paper with a title that was kind of defiant even, right? So challenging the empirical mean and the empirical variance, a deviation study. But I think that for many people who read this at the time, it gave you a feeling that you know, there is a big conspiracy trying to hide from us what the optimal estimators were, so we need to find out the truth, right? So, and then it's just to give you a list of people who have worked on such problems. I mean, there's lots of people, there are lots of papers, especially in more recent years. But then there's another related question. So as I said, well, the Catoni's problem, right? He was the one who formulated this problem at least in one dimension. And you're looking at, you take an n, you take a delta, you want the smallest possible error with probability 1 minus delta, right? Your challenge here is to avoid somehow the heavy tails that random variables can have, even though they have finite variance, right? You can do funny things with them somehow. But there is another setting that's somehow even more challenging, is what people call data contamination. well, some people talk about outliers in data, right? So points that don't seem to belong to the sample. How do you formalize that? Well, one way to do it is just to say, well, you have your IDs, and the only constraint that you have is that the number of xi's that differ in the contaminated sample from the original ones is at most epsilon times n. So at most, a fraction epsilon of your sample has been contaminated.
Oh, this is not contamination, but just error of containment, right?
Yeah, you could say, yeah, I mean, they call it adversarial just because, you know, the sample was generated by standard means, let's say, well, it comes from nature, but then somebody comes up, they know what estimator you're using, and they think, aha, I think that if I take these 2 points and throw them away to infinity and maybe take this other point and replace it by 0, I'm going to completely screw up the estimator. So at least that's a possibility in this model, right? So you can call it also kind of the paranoid contamination model, where you think that really the world's against you, and but there is a constraint to how bad the world could be. And let me show an estimator that works very well in one dimension. I mean, it's a classical estimator. So it's just, it's called the trim mean. You order your sample points, the contaminated sample points. And instead of taking the simple average, you throw away the t smallest and the t largest points, and you compute the simple average of what's left. Right, there's a constraint on t. T has to be less than n over 2, otherwise you're throwing everything away. But this, I think, makes sense, right? So, I mean, it makes so much sense that they use in the samba school context in Rio. Always throw away the lowest grade and the highest grade, right? So this has clear practical applications. But, right, so this is an estimator, and I mean, there's a lot of classical work in the field called robust statistics on this estimator and related constructions. But this apparently had to wait for, well, Paulo Zoraida, who was one of the co-authors of the present paper, and myself, that we looked at this from a finite sample perspective, right? So somehow motivated by Cantonese developments. And then it tells you that if you choose the trimming level, right, how many things you're going to throw out on the left and on the right. If you choose that correctly, then you get a bound of the kind you're looking for, which is maybe not exactly the right bound because the constant's not right? This is a universal constant. But it gives you the sub-Gaussian bound, right? Remember the sigma, then you have square root of log 1 over delta divided by square root of n. And it also somehow takes care of the contamination. I mean, this is a bit hard to read, but it's basically saying, okay, fix a p, right? So you're saying, okay, assume that the LP norm of x minus mu is finite. And this is saying that the price you pay for contamination is this LP norm times epsilon raised to 1 minus 1 over p. And, well, we call this a contamination term. This is a random fluctuations term. It turns out that both terms in this bound are optimal up to the constant. You can show that no estimator can do better. So somehow the trim mean, which is an estimator that's been around for a long time, is optimal in this sense. What does optimality mean here? It means that if you fix the family of distributions with a given sigma and with given values for these LP norms, I can prove that for any estimator, there's going to be some data distribution that's going to saturate this bound up to the value of c. Okay, but now we want to estimate Fréchet means, right? So we should be able to extend this construction somehow. We need to. So let's first go to a space we understand relatively well that still has a kind of, explicit geometry, which is RK with a Euclidean norm. And then it's a simple exercise to show that suppose I tell you there's a vector mu here. I'm not going to tell you what mu is, but I'm going to give you an estimate of the inner product between mu and v for each vector v in the unit sphere. And this estimate is correct up to an error, eta or whatever, right? So from that, I claim that you can recover the vector mu just from this inner product information up to an error that's 2 eta. So 2 times the worst case error for the one-dimensional directions. I'm not going to prove this here, but it's a nice little exercise. So basically, what we did was, okay, somehow, if you want to estimate these inner products, you just use trim means in all possible directions, right? These one-dimensional trim means, right? And then somehow you put this information together to estimate the actual vector mu. And this is the error bound that you get. So this is originally Gabor and Shah Mendelssohn. Then we had a slightly different proof that also somehow extended to other norms. And this is the result that you get. So it's there are two terms that are somehow familiar, right? So this lambda max is the largest eigenvalue of the covariance matrix, which is really the largest variance over all one-dimensional projections of the vector x. So this is like the sigma square root of log 1 over delta divided by n that we had before. This is the same thing with the LP norms for the contamination. So let me just move on here. And okay, sorry, I should come back here. But you look at the LP norms over one-dimensional projections. So somehow the effects here are purely, now let me say, between scare quotes. This is a dimension-free term. This is also dimension-free. Only cares about one-dimensional directions. But then there's a term that cares about the full structure, which is this trace of the covariance matrix. And this is somehow people call the complexity term is, okay, this comes from the worst case one-dimensional direction. This comes from the worst case one-dimensional direction. This comes from just estimating the vector in all directions at once, somehow. That's the intuition. And you can see that these guys can have different orders of magnitude if your covariance is isotropic, right? It's just a multiple of the identity. So this complexity term carries a dimension, and the other terms don't have anything to do with it. Okay? So somehow this is important, I mean, for the theory, that log 1 over delta and k are separate. That you can get very high confidence without paying a dimensional price for them. And the problem that we have with this, I mean, there's a talk about Fréchet means, right? It's taken me a while to actually get to them. The problem we have with this is that there's no obvious way to generalize this construction to arbitrary metric spaces, right? Because I'm using the linear structure of RK.
But do you use on symmetric or not?
What was that?
Does it depend on the choice of medium metric significantly or not?
So the same estimator that we have somehow works for any norm that you put in RK. But then you need to replace the unit ball or the unit sphere, right, by the unit sphere of the dual norm. And then you get bounds that depend on parameters according to that norm. So you're not going to get exactly the covariance matrix or these parameters. You're going to get other things, but you still get some result. I mean, one important point is that we can show that somehow what we get for any norm is optimal or nearly optimal. So there's no, I mean, if you fix a norm, then you cannot do much better than this. But let me just move on. So now we're going to talk about what kinds of geometrical conditions we need on our spaces to be able to estimate the Fréchet mean well. Okay? And somehow it has to do, I mean, there are lots of work on this topic. I'm going to try to keep it short, but there's very interesting stuff going on here. If you're interested, you can check these references. So what's the problem with analyzing a Fréchet mean over a metric space? Well, just the sample Fréchet mean, okay? That one where you minimize this function of that's the average of distances squared to from xi to c. What's the problem with that? Is that there's no explicit formula for the estimator, right? Of course, when you're including space, the minimizer here is just the average of x sub I. So in Hilbert space, say also, that's true. But let's try to analyze this without using the explicit formula, right? Because maybe that gives us some intuition of what comes next. Well, one thing you can do, which is very typical from statistics, you just notice, well, a minimizer has to minimize, right? Minimizer's got to minimize. So if you look at the sum, right, distance squared, this average, and you compare to what you get with mu, this has to be less than or equal to 0, right? So this is the sample minimizer, not the actual mean. And now you can write down, you can expand this thing, you get the distance between mu hat n and mu, and here you get it in a product term. So you get, right, you start writing equations, you get this thing, you move the average inside the inner product, and now you use Cauchy-Schwarz, and you get a nice little expression which is like 0 greater than the distance squared minus 2 times the distance times this other norm here. You work this out and you get this bound. Well, I call it a pointwise bound because there's no probability here, right? This holds for all points in your probability space. Of course, this bound is completely preposterous because here I have the sample mean under this guy. So mu hat n is exactly this average here. So I'm saying that the distance between mu hat n minus mu is less than 4 times the distance, well, the distance squared less than 4 times the distance between mu hat n minus mu squared. So this is completely preposterous, but the good thing about this is that this somehow generalizes. And then, you know, sometimes we do mathematics by wishful thinking. You can start thinking, okay, let me just mention one more thing here, sorry, which is once you get to this point, you reduce the problem of estimating the behavior of the sample mean to an i.i.d. sum, right, of vectors that have mean 0. And that's the kind of thing that's the bread and butter of probability, right? So we know how to analyze these things very well. And then you can get bounds in expectation, concentration, all sorts of things. But the question is, can we somehow generalize this strategy to more general spaces, right? And let me give you a setting. Right, so what kind of generalization are we looking for? So let me just jump this because it's going to be easier. I'm just going to move on now to Riemannian manifolds. And it'll turn out that things having to do with tangent spaces and whatnot, they're going to give us conditions that allow for this proof to go through. Okay? Okay, so quick recap, right? So we have a Riemannian fold with a Riemannian metric. So at each point you have a tangent space. It has an inner product and a norm. I'm going to be talking about the log map a lot. The log map takes, you know, there's the exponential map mapping the tangent space to the point along the geodesic with the tangent vector. There's a map that comes back, right? So this map is not well defined for certain points, but we don't care. I mean, one advantage of doing probability over differential geometry is that things of measure 0 don't matter. So the cut locus, you can prove that it always has measure 0. Okay? Not obvious, or at least if you're sitting at the right point P here, as we're going to see later. But the log point then, it maps points in X to vectors in tangent space that corresponds, right? The log P of Y is the tangent vector of the geodesic connecting P to Y. And then you have this distance property here. And here's something that happens for certain manifolds or certain subsets of manifolds, that you can write an expression that's very similar to what we had before for the Euclidean norm with an extra constant factor here, involving the tangent space somehow. Okay, let me show you. Okay, so the difference here is that you get this extra, you get an inequality here. Before we had an inequality, right? So for these kind of parallelogram-like things, I have an inequality and I have a constant here. And here you have, but let me jump here. So if you're talking about manifolds with non-positive sectional curvature at all points, so you have this exact expression here, which you can manipulate as before. So you, I mean, we can do sort of the same tricks as before. And Carl Theodor Sturm, he actually proved that this property here is equivalent. If you have this property for all points, etc., this is equivalent to having non-positive sectional curvature at all points. Okay. And then you have something else too, which comes from the right. So you're looking at mu that minimizes this expression. You can work out what the first order optimality condition is for his. Well, it turns out that the gradient of this functional is this guy, and the gradient has to be 0 at a minimizer, so you get this extra condition here. Why is this important? Because remember, I'm going to be adding these things up, if I try to come up with bounds, so I want to get a sum of vectors that means 0. But I mean, we're going to be talking about examples where you have constants that are not exactly 1 here, so they're more general somehow. And let me give you, and even from that, you can sort of replicate the calculation that we did in Euclidean space, and you can get a bound that now has this extra factor, right? So let me, okay, sorry that I keep switching the slides, but let me make sure. So first order optimality is always going to be true. And then under some kind of curvature condition of restriction on the support of the distribution, you're going to have something like this. And from this, you can work and get a bound like this. So the distance from the Fréchet mean to mu squared can be bounded by the norm squared of a bunch of random vectors that have mean 0 and have the same distribution. So, okay, how do we get this condition when you don't have non-positive sectional curvature, right? So before I was talking about things that are flat or negatively curved. What if you have positive curvature? So there is a sufficient condition that comes out from the work of Legouis, Paris, Rigolet, and Strom, LPRS, which is, well, sorry for the typo here, which is this. So you have a manifold of negative curvature, so potentially positively curved. But if you're somehow so I'm not going to be looking at the whole manifold now. I'm going to be looking at a subset, a geodesically convex subset, right? A subset where you can connect everybody by geodesics. And then you have this condition, which is, I mean, maybe easier to explain in an example, but I'm saying I need a subset that's small enough, so if I take any 2 points and connect by a geodesic, a length minimizing geodesic, I need to be able to extend this geodesic at both ends without leaving the set I'm working with. Okay? Or for all points in the support of my probability measure, or something like that. So basically the condition is this, so that if I can take any length minimizing constant speed geodesic and extend it a bit on both sides, then I get a lower bound of this parameter.
So that's a property of the metric space, correct?
That's a property of the metric space. It's not going to hold for a whole manifold of positive curvature, right? On the sphere, but I mean, it's easy to see an example. So this is a property that, for instance, you have here, right? I'm being a bit imprecise here because really I should be saying X is a subset of a larger metric space, and I need the geodesics in X to be bi-extendable in this sense in this larger geodesic space.
Lambda in and lambda out, they can be different for different values of gamma with no control.
Yeah, so what I'm saying is that if I get lambda in, lambda out, they work uniformly for all geodesics starting from my Fréchet mean, then I get this result.
Okay.
Right. Yeah, so I need uniform bound. So it's a very strong condition. So if I want this to hold, I need this bi-extendability condition to hold for all geodesics stemming from mu to points on the support of my probability distribution. So you should think that X is not the whole manifold, but it's really the support of the probability distribution that I'm working with. And maybe the geodesic hull of this support. Okay. Okay, so but on the circle things are easy to see. If you look at a small set like this, all geodesics are bi-extendable. This somehow looks like Donald Trump to me. I don't know why. I mean, but if you look at a set that contains 2 antipodal points, then of course a length minimizing geodesic is not extendable, right? You move a little bit to the, say you have this half of the circle, you extend a little bit, now you have a shorter geodesic on the other side, right? So, but the main point, remember that I told you that I wanted to work with Wasserstein space. Wasserstein space is certainly not a manifold. It's an infinite dimensional object. It has some properties of a manifold. Somehow people like talking about Riemannian calculus there, but it's certainly not a bona fide manifold in any way. But there's a whole theory of metric spaces that somehow behave for some practical purposes like manifolds. And these are called Alexandrov spaces. I mean, there's a recent AMS book on this topic. I mean, many people have worked on this. Petrunin, Gromov, Perelman, many people in geometry have looked at these things.
So it's Alexandrov.
Yes. And I want to blame this on the autocorrect, but I'm not sure I can. But anyway. So what's an Alexandrov space? So it's a space where you look, well, first of all, for any 2 points, you should have a length minimizing curve whose length is equal to the distance. I'm not going to explain what the length of the curve in a metric space is, but you can try to guess. So these metric spaces where you always have curves of connecting points that have length equal to the distance, they are called geodesic metric spaces. But you need an extra condition, which is maybe easier to see on the picture. I mean, the main point is that under this condition, you can have some sort of first order calculus on your manifold and make everything that I said make sense. What is the condition? So I'm going to be talking here just about non-positive and non-negative curvature, right? So this, of course, is zero curvature. This is positive curvature. This is negative curvature. What does it mean to have positive curvature? It means that if I draw a triangle in this space, I draw a triangle here, and the triangle on the left is wider. What does it mean that it's wider? So I take 1 point on some side of the triangle, find the corresponding point here. What's the corresponding point? Well, I just want the distances here to match the distances here. And I want to say that the distance to the opposite vertex is bigger in positive curvature than in zero curvature. So I say that a metric space has no negative curvature if for any geodesic triangle that's small enough, I take the Euclidean comparsor triangle, and the triangle here is wider than the triangle here in this precise sense. Well, negative curvature is a sense if I replace wider by narrower, right? Or maybe I should say at least as wide or at least as narrow. Because, right? So there's a very beautiful theory to these spaces. And it turns out that a Wasserstein space with this Wasserstein metric is non-negatively curved. And now we come to this theorem that I mentioned. I mean, here I wrote it in kind of, I thought I had it in more analytical language. But basically, okay, this is called the probabilistic statement. If I want to find the optimal transport map, remember that this metric somehow has to do with the optimal displacement cost from moving to mu to p. And if I want to find the optimal displacement map, it always, I mean, a map mapping taking mu to p is optimal if and only if it's the gradient of a convex function. That's a very beautiful result. And it's, so based on this, so we have in a very explicit form, somehow this gives you an explicit form for the geodesics in this space as well. And we know it's non-negatively curved from previous work. And what Lewy, Paris, Rigollet, and Strom showed is that if you take a subset of this Wasserstein space that consists of deformations of a certain base measure mu, right? Deformations by maps of this form, and these maps are sufficiently nice. Basically, you're asking that this is a bit weaker, but one way to think of this condition is saying, I look at the Hessian of the convex function v, and I want its eigenvalues to be between beta and alpha at all points. Right? You can go a bit beyond that, but that's sort of the gist of the idea here. And then, if you have a constraint on alpha and beta, then you get a lower bound of this all-important parameter that allows us to carry out the calculations. So this is a strong constraint. It's not clear it's optimal. It's clear that some constraint is needed. But it's at least it covers many interesting cases from the point of view of applications if you look at kind of small deformations of objects in some sense, or smooth enough deformations of objects, right? So I mean, small comes with a caveat here because somehow this beta and alpha don't change at all if you add a translation to your function to the gradient of v, right? So you can translate by a lot, but you cannot deform by much. So okay, I can finally explain to you what's the estimator that we have and what kinds of results we get in my remaining 2 minutes, I think. So now we have this abstract framework where somehow we get this strong convexity in Alexandrov spaces. We have this formula, all sorts of nice properties. We have something like a tangent space in Alexandrov spaces. We can do things. It's much more complicated than on the manifold, but it can do something. And these are the kinds of bounds that people get in previous work under very strong assumptions. Well, they get bounds in expectation under weak assumptions. To get concentration bounds like the ones we want, they get something that takes this form, which is not too bad because it has a 1 over delta. But you make a very strong moment assumption of the distance. And you get something that in Hilbert spaces is very far from being optimal because somehow I have an interaction between this 1 over delta and the trace. The trace is a dimensional factor and can give you all sorts of trouble. And these things are also not going to be robust to the sort of adversarial contamination that I talked about. Okay, so the optimal, this is just to recall the optimal rate for Hilbert spaces. Here I have a trace, here I have lambda max, and here I don't have that, right? So I have trace times log 1 over delta. Okay, so what do we do to generalize the trim mean to a metric space? We use the trim mean somehow to compare two points in a metric space. So A and B are sort of my two candidates, or 2 points on my metric space. I want to know which one of them is kind of passes better for shimmy or not. So to compare them, I'm going to look at this thing here. Distance squared from xi, well, this is a contaminated sample as before. Distance squared from xi epsilon to A minus distance squared xi epsilon to B. And I take the trim mean of these quantities, right, over the contaminated sample. This gives me a number for each A and B. And now my Fréchet mean estimator is going to be like this. So to each number A, I attach a number that's simply the soup of this thing of all points B in my metric space. And then this gives me a function of A, and I minimize this function of A to find the estimator. How do you do this in practice? Well, I mean, there are heuristics that seem to work whenever I have gradients, but we didn't try too hard to break them, so we don't have a good theory for how to compute this thing. No rigorous results saying that, something converges to these. But in any case, we can prove this result. That's really a perfect generalization of what people know for Hilbert spaces. And it turns out that the thing that plays the role of the covariance matrix in this result, right? So remember in Hilbert spaces we have covariances. in non-Hilbert things, we still have vectors in the tangent space, and they're vectors in the Hilbert space, so they have a covariance matrix. And somehow this thing here is equal to the trace of the covariance matrix, which is what we have in Hilbert spaces. This thing here is simply the largest eigenvalue of the covariance matrix of log of x at the Fréchet mean. And here we have the one-dimensional terms that we had before, the contamination term. So yeah, I'm going to completely skip the proof. Let me just say that in the specific case of the Wasserstein space, we're able to improve the previous bounds by things that, well, maybe they don't matter too much for a fixed delta, but if you want to go to a high confidence setting where delta can be very small, then you don't want this to be multiplied by the dimension of the MN space. You want these things to be separate, and we're able to achieve that. And we have, good results against contamination. So let me just, I have basically minus 2 minutes. Let me just jump and say that maybe the main problem there, the main gap we have in our analysis right now is that we really don't know much about what happens if you don't have these favorable convexity type properties, right? So, and especially in Wasserstein space, it's clear that things are, you're not going to have such nice properties if you move away a little bit from this perturbative regime. So it's unclear what the boundary between, there are settings where we can get results. There are settings we know that such results cannot be proven. They're not going to be true. But there's a lot in between them. So let me stop here and thank you for attention.
Thank you, Roberto. So we have time for one or two questions. Oh, I have a quick question. So this is really interesting work. A lot of what you do assumes you know a lot about the contamination structure in your data. Is it easy to disregard this knowledge?
So it's one of those things, right? So we wanted to have a clean mathematical statement, and it seems in order to have that, you sort of need to have a good guess for what this epsilon is, right? So in practice, what people what they'll do is kind of look at the data and say, well, this should be epsilon equal to 0.01. So I don't have a theoretically grounded recipe for kind of estimating epsilon from data. And this is actually a problem with this whole line of work. It's something that people simply don't know how to do. But it would be very interesting, of course. Right? So I think that, at some point, I think we could show that with, significantly stronger assumptions, we could do something. But it doesn't quite give the optimal bounds back. So it's not clear if we can kind of somehow estimate epsilon from the data and get the kind of optimal bounds that I presented.
Questions? So let's thank our speaker again.